All right, today we're going to go on a little journey together. It's a story that starts with just a tiny little wobble and ends with all the music, the voices, and the noises that make up our world. We're going to follow the amazing path of a single sound, all the way from a vibration to the experience of hearing it inside your head. So, let's dive in.
Have you ever really stopped to think about it? How does something happening all the way across the room, say a book falling off a shelf, somehow travel through thin air and become this clear, recognizable event inside your brain? It's kind of wild, isn't it?
Okay, so to really get our heads around this, we have to go right back to the very beginning. What even is a sound at its most basic level?
Well, it turns out that every sound you've ever heard, and ever will hear, starts with this one simple thing: a vibration. Something somewhere is moving back and forth. A guitar string, your own vocal cords, or this tuning fork right here. As it wiggles, it physically pushes on the air particles right next to it, kicking off a fantastic chain reaction.
So what does that chain reaction actually look like? Well, as the tuning fork pushes forward, it squishes air particles together, creating these little pockets of high pressure. We call those compressions. Then, as it moves back, it leaves a gap, an area of low pressure called a rarefaction. This constant push and pull, this pattern of squish and stretch, that is the sound wave. And in physics, this has a very specific name. It's a longitudinal wave. Now, here's the key thing to get. The individual air particles themselves aren't flying across the room to your ear. No, they're just kind of wiggling back and forth on the spot, bumping into their neighbors, who then bump into their neighbors. It's like a domino effect, passing energy along the line. Okay, so we've got this wave of pressure. But how does it actually get from point A to point B? That's the next leg of its journey. So here's a crucial point. Those particles we've been talking about are absolutely essential. Sound needs something to travel through, a medium. It could be air, water, or even a solid object. And hey, this is why those big, silent explosions you see in space movies are actually scientifically correct. In the vacuum of space, there are no particles to carry the wave. So, no particles, no sound. It's as simple as that. And the type of medium it's traveling through makes a huge difference. In a gas like air, the particles are all spread out and far apart, so passing that vibration along is a pretty slow process. But in a solid, where all the particles are packed in tight, that vibration can be passed from one to the next almost instantly.
Just how fast are we talking? Well, get this. In aluminum, a sound wave zips along at over 6,000 meters per second. That is almost 19 times faster than it travels through the air that you're breathing right now. It's just unbelievably quick.
You can really see the difference across different materials here. Look at aluminum way up at the top, then glass, then even water is way faster than air. You see the pattern, right? The denser the medium, the more tightly packed the particles are, the faster the sound travels.
Of course, a sound wave doesn't just travel in a straight line forever. When it hits a surface, like a big wall in an empty hall, it can bounce right off. And that reflected sound wave, the one that travels all the way back to your ears, well, that's what we call an echo.
So we know what sound is and how it travels, but why does a high-pitched whistle sound so different from a low, deep rumble? Well, that brings us to the actual properties of the wave itself.
Really, it all comes down to two main things. You've got pitch, which is all about frequency, basically how many waves pass by a certain point every second. The more waves, the higher the pitch. Then you've got loudness. That's all about amplitude, which is just the size or the intensity of the wave. A bigger, more powerful wave means a louder sound.
And this is a perfect way to picture it. Look at the waves on the left. They're all scrunched up close together. That's a high frequency, and your brain hears it as a high pitch. Now look to the right. Those waves are way taller, more powerful. That's a large amplitude, and that's what you hear as a loud sound. The very shape of the wave directly translates to what you hear.
But what's really fascinating is that our own human hearing is, well, it's pretty limited. A healthy human ear can hear frequencies up to about 20,000 hertz. But compare that to a dog, who can hear things more than twice as high-pitched as we can, or a dolphin. Their hearing sounds 10 times higher than our absolute limit. The world is just full of sounds that we're completely deaf to.
So this leads to a really cool idea. If there are all these sound waves out there that are beyond our range of hearing, could we somehow put them to work?
And the answer is yes, absolutely. It's called ultrasound. It's just sound with a frequency that's too high for our ears to pick up. We can't hear it,
But we can generate it, we can control it, and we can use its properties in some truly amazing ways.
And this might be the most incredible application of all. By sending these silent, high-frequency waves into the human body and then reading their echoes as they bounce back, we can actually build a picture. This technology, based on the simple physics of a sound wave, lets us see the very beginning of a new life. It's just profound.
Okay, so our wave has been created, it's traveled through the air, and now it has finally reached its final destination, the human ear. So how does this physical pressure wave turn into something our brain can actually understand?
Well, it's a brilliant four-step process, part mechanical, part biological. First, your outer ear acts like a funnel and captures the wave. Second, that wave travels down and hits the eardrum, making it vibrate. Third, and this is so cool, 3 of the tiniest bones in your body act like little levers to amplify that vibration. And finally, a tiny snail-shaped part called the cochlea translates it all into an electrical signal that the brain can finally interpret as sound. And here's a look at that whole amazing system. I mean, from the outer ear canal to those tiny little bones, the hammer, anvil, and stirrup, all the way to the cochlea and the auditory nerve, it is an absolutely astonishing and elegant piece of natural engineering.
So let's just recap that whole journey. Sound starts as a vibration. It travels as a pressure wave that needs some kind of medium. Its pitch and loudness are determined by its frequency and amplitude. And at the end of the line, our ears translate those waves into everything we hear. That's the entire life of a sound, from physics to perception.
But that leaves us with one last, kind of philosophical question to chew on. You know the old saying, if a tree falls in a forest and no one is around to hear it, does it make a sound? Well, we know it definitely creates a pressure wave. That's just physics. But does it make a sound? When does a simple wave of vibrating particles cross that line to become the rich experience we call hearing? That's something to ponder.